Today, we will see in detail about the stationary state. Before going into the detail, kindly subscribe my channel in order to get updates. My channel ID is youtube.com/at Vasuv See, first we will see what is the stationary state. That is separable solution of the total wave function psi, which is a function of x and t, are called stationary state. That is, after separating the variable x and t, we will get some solution. That state is called stationary state. You know very well that Schrodinger equation is IH cross delta psi over delta t, which is equal to H cross square over 2m delta 2 psi over delta x2 plus v of x multiplied with psi, which is a function of x and t. Here you notice that this v of x is independent of time. It is depends only on x. This is a one-dimensional Schrodinger wave equation. So this Schrodinger equation admits a considerable simplification when potential energy V of x is x does not depends on time. So if V is independent of time, then your solution is very much simplified. Here only the complicated parameter is potential energy, that is V of x. It is then possible to express its general solution as a sum of product of wave function x and t separately. That you have to realize x and t separately. Now you substitute or replace psi of x and t, which is equal to u of x and f of t in the above equation. That is in this equation. Here we have separated the total wave function into two parts. That is x component, wave function of x component is u and wave function of t component is f. So you just substitute here. Ux does not depends on time, so you can take it out because this is first order time derivative. Then it will become tf of t over tt, which is equal to this one. Here, you are taking second order derivative of x, so you can bring only the u, wave function u inside. F of t, it does not depends on x, so I have taken it outside. So just now we got this expression. Just divide it by ux f of t. So in the left hand side, ux will cancel with this ux and you will get only f of t. So here you will get the right hand side ih cross over f of t into delta f of t over delta t. Similarly, the right hand side will become this f of t will get cancelled with this f of t. So you will get only u of x because you are divided by u of x f of t. Here, you just to notice that the left hand side is purely depends on time, and the right hand side purely depends on the position. By changing the time, the right hand side of the equation will not get affected. Similarly, by changing the x, left hand side will not get affected. It is possible only if you have a common constant for both right hand side and left hand side. That constant you take it as E, that is called energy eigenvalue. Simply you take this dimension of f of t will get cancelled with this f of t. Here only the term is h cross over t. This is h cross over t. H cross over t is having the dimension of energy. So naturally, this E must be the energy level. Similarly, the right hand side, if you take the right hand side, you will get E because it must be the same E. So, as I said, left hand side will not get affected by changing X. Similarly, the right hand side will not affect by changing the T. Both are independent. Just now, we have seen by taking into the consideration of left-hand side of the equation, that is IH cross over f of t into delta f of t over delta t is equal to E. That is delta f of t over delta t is equal to H cross f of t, which is equal to here I have brought this IH cross f of t to the right hand side. So this IH cross comes in the denominator and this f of t comes into the numerator. Now what I am doing it just to multiply and divide by I. So in the denominator you have I into I squared, which is equal to -1. So I have taken this minus. So this will be I over H cross f of t. Then the equation for f is readily integrated to q. So this we can obtain the immediate solution for this equation is f of t is a well-known solution. F of t is equal to a into e power minus I e t over h cross, where a is the normalization constant. If the wave function is normalized, then a is equal to 1. Then this equation will become e power minus I et over h cross. The total wave function psi, which is a function of x and t, is equal to u of x into f of t. We have seen f of t is equal to e power minus minus I e t over h cross, this red color bond. So I have replaced f of t by the red color bond exponential term. Now what I am going to do is I am going to find the value of IH cross, the time derivative IH cross times the time derivative of wave function, total wave function psi, which is a function of x and t, which is equal to, I have taken this IH cross as it is, IH cross as it is. Then I am going to differentiate this with respect to time. Here u of x, there is no time dependence. So I have taken u of x as it is. Here I have taken u of x as it is. Then you differentiate only the exponential term. Exponential term is minus IE over h cross. Here you can see if you differentiate the exponential term, you will get minus IE over h cross. Of course, the exponential term also will appear here. Now you simplify this. That is, h cross will get cancelled with this h cross. H cross and h cross will get cancelled. And this I, here one I squared is -1. So minus of minus will become plus. So only term left is E. I have taken as it is. And you know very well, this is nothing but the total wave function. That is u of x. Uh, the exponential term and u of x is equal to the total wave function. That is this. This is the total wave function psi. This one. Uh, so we got the solution that IH cross IH cross times the partial time derivative of psi is equal to E psi. Here I have mentioned in the blue color font IH cross delta over delta t is nothing but the energy operator. You know very well-known energy operator. That is, if you operate IH cross delta over delta t over the wave function, then you will get the energy eigenvalue. So it is called energy operator. So just now we got this expression by considering the left hand side of the equation. The above equation is called eigenvalue equation, where as I said, IH cross delta over delta T is energy operator. If you operate the energy operator over the wave function, you will get energy eigenvalue E multiplied by the total wave function, which is a function of x and t. Uh, then if you take right hand side of the equation, you will get this one. This also we have seen already. That is minus h cross squared over 2m and delta 2 u over delta x2 plus v of x u of x is multiplied by 1 over u of x is equal to e. You just bring this u of x is to the right hand side, you will get this one. Now you just multiply by f of t, then you will get this. Here you can notice that this is the total wave function psi. This is also total wave function psi, which we are going to see now in detail. As I said, this u f of t, and here in the right hand side u f of t is the total wave function. I have replaced this by the total wave function psi x of t and psi x of t, this answer. And the terms in the blue color bracket is nothing but your Hamiltonian operator. First term is related to first term is kinetic energy, and the second one is the potential energy. We have already seen that psi x of t is the eigenfunction of the operator with an eigenvalue E, that is the energy operator, IH cross delta by delta t. This is the energy operator. If you operate the wave function over this operator, you will get the energy eigenvalue E. Similarly, this one. If you operate the this energy operator, that is a Hamiltonian operator, minus h cross squared over 2m delta 2 over delta x2 plus v of x, then again you will get same eigenvalue E, which we have seen some couple of minutes ago, because the right hand side is fully depends on x, left hand side fully depends on t. Both are independent, so we will have a common constant which we have labeled as E. Now we will see the significance of the separation constant E. That is, we have separated this psi x of t into x component separately as u of x, where u is the wave function with respect to x component alone. This exponential term contains the time factor. If you take the product of psi star psi, that is complex conjugate of this, then you will get u star x e power, this I will become minus I will become plus I. Since e is a real number, so the complex of this e also e t over h cross. Then the u, this psi, the first two term is related to the complex conjugate of the wave function, that is this two depends on complex conjugate, and there's the last two term is the psi. This is the red color, underlined by red color is psi star, and green color is psi. So you know very well that the exponential term is number. You can interchange the number, so you can bring this to last. Because if it is an operator, you are not supposed to interchange. Since it's a number, I have taken this out. So this will get cancelled. That is, this exponential minus I and plus I will be equal to 1. So this right hand side will become modulus square of psi x of x and t, and sorry, left hand side will become modulus square of psi x of t, and right hand side will become u x of t, modulo squared u x of t. If you see this equation carefully, there is no time dependent part here. So the energy eigenfunction like the psi in the above equation said to represent a stationary state of the particle. Since the modulus square of psi is a constant with respect to time, this is constant with respect to time. We will see in detail now. Now we will see the variance of Hamiltonian operator. That is sigma h. H represents Hamiltonian operator. Sigma is variance, which is equal to the expectation value of h squared minus the expectation value of h and squared it. Square. First you take the expectation value of the h squared, then you subtract that from the expectation value of h squared. Now what is the expectation value of h squared, which is equal to, this can be written as in Dirac notation, uh, psi h multiplied with h. I have written h squared as h into h into psi. If you H act on psi, it will give energy eigenfunction E, which is a number. So I have taken it out. So this will become E psi H psi. Then again, when H operate on psi, you will get energy eigenvalue E, which is equal to E squared, the inner product of psi with psi. Due to orthonormal property, psi with psi is equal to 1. So this will become E squared. So the expectation value of H squared is E squared. The first term is E squared. Similarly, what about H, expectation value of H, which is equal to psi H psi. So when H operator, Hamiltonian operator act on psi, you will get the energy eigenvalue E, which is a number, you can take it out. So the expectation value of H is equal to E. So the square of it is E squared. So E squared, the expectation value of H squared is E squared. The expectation value of H power 2 is equal to E squared. So both will get cancelled, which is equal to 0. Hence, the solution to Schrodinger equation obtained by the separation of variable is a constant and has a finite value. So it has a constant and is a finite value. That is a very important point. Just now we have seen that the eigenvalue of the wave function is for stationary state is fixed, is a finite one. Uh, so now the wave function can be written as the linear combination of wave function, which is the solution for En. Individual wave component can be written as usual size of n, and with the expansion coefficient an. That is the total wave function can be written as linear combination of so many wave function where n is equal to 1 to infinite, n tends to 1 to infinite. Now psi of psi n can be written as unx e power I ent over h cross. So this is the usual way of writing the linear combination. Here, then what about the expectation value? You know that also well defined. The expectation value of Hamiltonian is equal to the summation over 1 to infinite um, uh, modulus square of an into en. That is when you, if you operate the Hamiltonian operator over this total wave function, you will get En. So here you must notice that En, where An modulus An squared is nothing but the probability. So each energy state have different probability. Hence, this is has the variances differ for each wave function, that is each eigenvalue. En is this is a weighting factor, that is a weighted average, that is probability. Probability times the energy state. Naturally, the nth energy state depends on this probability an modulus squared. So, for each energy value En, this will be different. That is, probability is different. So, if you add all the probability, you will get 1. So, ultimately, you can realize that the total wave function, energy eigenvalue of total wave function is fixed, is it is a constant one. However, for individual component, it varies due to this factor probability. Thank you very much for watching my videos and supporting me continuously. Uh, Kindly subscribe my channel. My YouTube channel ID is youtube.com/@vasuvp6. Thank you.